Yes, thank you very much. And I thank the organizer to make it possible to talk. So this is the topic of my talk. And the contents, I will give an introduction, explanation why I'm interested in this model. Actually, in the second step, I will introduce this Gaspar-Gilbert model. And they suggested a two-step strategy to derive the heat equation, actually, from microscopic principles. Then I will give simplified models for step one. Step one is a dynamical systems task, a very interesting dynamical system problem. Step two is a probability theory project. And for that, we have results by Alex Grigo, Kostya Hanyin, and myself. If I have time, I will briefly tell about our results for step two. Okay, so this is the heat equation, which you know very well. Kappa, so T is the temperature, X is the spatial variable, and T is time. And T is temperature, and kappa, depending on the temperature, is the thermal conductivity in the equation. So this is the usual diffusion equation where the diffusion coefficient depends on the temperature as it is in nature. For a wide class of models, kappa, the dependence of kappa on the temperature is square root. For example, for insulating materials, gases of weakly or rarely interacting particles. But there are other situations where the heat conductivity coefficient behaves completely differently. For example, there is a work of Derek and Peter Toth in progress where they derive this particular dependence on the temperature. Now, the Fourier of heat conduction is in the focus of interest of mathematical physicists. It has been for a long time. Since the late 60s, there are rigorous derivations for various models of this. And some very good surveys, which I recommend, are these two. And for me, the recent wave started when I started hearing David Ruel talking about this kind of problems. He was applying linear response theory, and actually I keep hearing his talks, and there is a progress, but the progress is slow. Now, his approach is related to the differentiability of SRB states, and Dolgopyat added a very nice paper in 2004 to this problem, the differentiability of SRB states. Now, my interest, probably you know, I worked a lot on billiards. Billiards serve as a very good mechanical model for various phenomena of physics. And so actually, if I am talking about physical problems and the heat conduction diffusion, I am now talking also always about classical physics, not quantum. There is also a quantum direction in everything. Now, billiard models had a lot of successes in deriving diffusion, superdiffusion, these kind of things. But for heat transfer, it's just at the beginning, but it seems to be the most promising model. There are also models, oscillators, which is a different kind of thing. And so far it seems that oscillator models cannot start with microscopic Hamiltonian description. They always need some randomness. So that's why dynamical systems is basic in the problem, because we start from the Hamiltonian dynamics. Okay, so two important papers, Ekman and Young, they were trying to understand the behavior of non-equilibrium steady states. For example, if you have a slab, on one hand you have temperature T1, on the other hand you have temperature T2, and you want to understand what happens between the two boundaries. What is the temperature, for example, in the middle? It's not so simple as it sounds. So it's really a difficult theoretical question. So this is Ekman and Young. Actually, I want to say that we had a paper also about heat transfer for a very simple model, random walks with internet states, where we also use this kind of approach, that we put some phenomenological assumptions, and then under them we were deriving temperature profile, again by assuming different temperatures and the boundaries. But the real model I am going to talk about is a model introduced by two Belgian physicists, Pierre Gaspard and Thomas Gilbert, a model of localized hard disk. And for this model, they were suggesting a two-step approach. I jump ahead. So this is a part of the model. So you should imagine that this kind of model you have on the whole line. So you continue this model periodically to the whole line. So it's a quasi one-dimensional model. The gray circles are fixed, they are scatterers, and the white ones are moving disks, but the geometric sizes of the model are determined in such a way that the disks cannot leave the cells, but they can interact through these throats. Okay? So this is actually the model. For this kind of models, ergodicity was proven in 91, 92 by Bunimovic, Pellegrinotti, Suhov, and Liverani. So it's already known the model having good ergodic properties. And in this model, as you feel, there is no mass transport because the moving particles are localized. And of course, you can also imagine the analogous system in higher dimensions, 3 dimension and more. So you take a chain of similar chain in 3 or 4 or higher dimensions. And actually, in a recent paper, these models are interesting also from the physical point of view. In a recent paper, you see this kind of, the lack of mass transport appears in a nanostructured porous silica materials, and I also have some other references. Okay, so now this is the model, and I return to the two-step approach of Gaspard and Gilbert. The first step, you start from the full kinetic description, Hamiltonian description of an N-chain. At first, you derive from the microscopic kinetic equation a mesoscopic, so-called master equation, because in the first part, microscopic description, all the positions of the particles and velocities, they come into the equation. And then in the mesoscopic description, you forget about the details. You only keep the energies of the n particles. So you forget a lot of coordinates. You reduce the number of degrees of freedom of the model. And for the energies, you get a Markov process of interacting particles, n energies. And this is the mesoscopic. So you get a Markov jump process, actually, because when two disks or spheres interact, then the energies jump. So this is the explanation. And you will see that we will consider this model in the rare interaction limit. And this is why we get a Markov-Jahn process. Now, the second step, you already start from the mesoscopic equation, and then from it, by using probabilistic tools, you derive a hydrodynamic limit transition. You get we hope to get the heat equation. Okay, now I return to the model of Gaspar and Gilbert. So it's also important in their approach, the geometric parameters of the model. I introduce it in two-dimensional case. Of course, higher dimensional case, you can do it in the same way. So I assume that the box size is 1. We assume that we have periodic boundary conditions along the y-axis. It's not so much important. You mean in this direction you have periodic boundary conditions. The notations, the radius of the fixed scatterers of the shaded circles is rho f. The radius of the moving disk is equal to rho m. The condition of confinement, this is simple geometry, condition of the confinement is here, and the condition of conductivity, I mean, there is the condition that two neighboring disks can really interact. And for that, this is the condition. There is a critical value when they cannot really hit each other, they can just touch each other. So there is only one point of tangency between them. And this is the critical rho. So it's natural to introduce epsilon as a small parameter, rho m minus rho critical. Now, I told you that this model was known already to be ergodic. Nevertheless, Gaspar and Gilbert introduced a sort of simple but important new idea that if you keep the sum of the two radii fixed, then what happens? Actually, this whole system can be understood as a coupled map lattice, right? At every lattice point, you have some dynamical systems, and then at some points, you have an interaction between the neighboring things. So, but I make one more remark. So, look, if you consider one cell here, and the motion of this disk in the cell is isomorphic to the following billiard problem. You take only the center of the moving disk, and you increase the radius of this scatterer, of the fixed scatterer, by the amount of the radius of the moving disk. Then you get a billiard. You can imagine you get larger scatterers and the point particle moving. And the two systems, it's easy to see that they are isomorphic. So this disk system and the point particle billiard are isomorphic. Now, if you keep this sum fixed, then actually you have, for the critical value, you have n non-interacting billiards. And the configuration spaces of these billiards only depend on the sum of the two radii, and the phase space is 2. So this is the model, and the change only comes because there is a binary interaction of neighboring. So this is, in a sense, a simpler understanding of the same model, because you have a coupled map lattice, and epsilon is, corresponds to the radius of this binary interaction between neighboring particles. Okay, now this also belongs to the hint, or this is a physical equation. So this is the kinetic equation for n particle, which I was talking about. In symbolic notations, it is the following. So Pn is the density of the n particles in time. And then the time derivative is the sum of this expression. So this is the free motion. This is the interaction with the wall of the J's particle, free motion of the J's particle, and this is the binary interaction. Now, this red part, the binary interaction, this leads to the energy transferred. And I also denote the binary collision rate by nu binary epsilon. Okay, so what Gaspar and Gilbert were suggesting was the following. So when epsilon tends to 0, the small parameter tends to 0, then the rate of the binary interaction tends to 0. There is less and less chance for neighboring particles collide. During this time, each particle collides with the wall with a fixed density. So this density is still a positive constant, approximately positive constant. So there are two scales. There is a scale which governs the in-cell motion, and there is a rate which governs the binary, the interactions. And it tends to 0. This is why it's called, it is the rare interaction. It's a rare interaction limit. So they actually derived the master equation for the density, and then they also made the hydrodynamic limit and obtained this constant times square root of T, the heat conductivity. Now, I tell you some sort of story. 2 years ago, I was giving a talk in Mexico, in Cuernavaca, on diffusion, super diffusion for billiard models, various billiard models. And Henrik Laralde, really an excellent computational physicist and a very nice person, after the talk, just friendly asked me, okay, so you mathematicians, why do you suffer so much when you know what the result will be? Okay, you can encounter this kind of opinion. That was really a friendly remark. I discussed the same question with Bastien Fernandez recently in Curran Institute, NY2. He's also a computational physicist. And he said that, well, in his opinion, the mathematical understanding of a subject is the true understanding. So I was happy to hear his opinion. But practically, so these very strong theoretical physicists, Gaspar and Gilbert, they derived on physical level, they realized the two steps of their approach. But Stefano Olla, for me at least in 2011, he explained that their derivation of the heat equation uses a symmetry argument which is not correct. So this also shows that mathematical understanding is the true understanding, because in the physical level you can make mistakes. And actually, who?
People that work like Landin,
Yeah, yeah.
They say that they can see more using this hydrodynamic model. It's not just
Yeah.
understand it. They use some kind of probabilistic argument to give that information on the solution of the PDE.
Yeah, yeah. Well,
Don't tell them that it's just for
okay,
to understand.
okay. Anyway, I also have other arguments for mathematics too, but okay. Anyway, so the physical derivation was incorrect, though these are very good physicists. And Makiko Sasada, a young Japanese mathematician, recently, so she has an unfinished manuscript, so it's also analytic or heuristic, where she really derives the heat equation from the master equation in a correct way, but it's still not a mathematical derivation. The mathematical derivation is still a hard question. Probably Landin could also work on it. Okay, so this is a real challenge to try to prove rigorously what Gaspar and Gilbert suggested. Actually, I can tell you two results which lead to this direction, though they do not complete at all. So the first thing is Keller-Liverani. We're considering the rare interaction limit, so a coupled map lattice where interval maps are coupled with collisions, collision-like interactions, meaning that it's a rare interaction, but when there is an interaction, it's a drastic interaction. It's not just something small. So, and this is the difficulty in the whole dynamical part of the problem. On the contrary, Dolgopiaty and Liverani were considering the weak interaction limit, so they were considering coupled map lattice, where the individual dynamics are beautiful hyperbolic Anosov dynamics, but the interaction is always acts the interaction, it's permanent, but it's weak. And as a limit, they obtained a system of interacting stochastic differential equations. Now, there are two other works in progress which are slightly related, not directly related to the Gaspar-Gilbert model. Dolgopiaty and Nandori, they work on deriving heat equation from periodic Lorentz process in a slab. So you take a periodic Lorentz process in a slab, and you have stochastic boundary conditions corresponding to different temperatures, and they derive the heat equation. And there is another work in progress where they consider also a slab and the sort of stochastic dynamics in a slab with different boundary conditions. They are trying to understand what temperature is actually in the middle of the model. Okay. Now I turn to our investigation, namely the starting point is a result which you may well know. So there are several nice papers about it. So if you have a dynamical system which is mixing in a control way, for example, alpha mixing, and you have a sequence of nice subsets in your phase space, nice subsets in a sense you want to avoid the neighborhoods of periodic points. And the probabilities, the measures of these small subsets tend to 0. Then the essence of these results is that the successive entrance time to these small subsets, they form a Poisson process actually on this time scale. This is not surprising result, but it's not easy to prove. Now, this is a sort of good philosophical introduction to our situation. Actually, I will only talk about this picture, 2 cells. Of course, you understand if you can handle 2 cells by methods of dynamical system, then you have a good chance to handle a fixed length chain of n particles. So 2 is the critical point. And so if you consider this model for 2 cells, with free boundary conditions along the x-axis, then this model is isomorphic to a 4-dimensional cylindrical billiard. Go back. So this is a 4-dimensional cylindrical billiard. Why? Because, as I said, that you can consider each in-cell dynamics as a billiard. And if you consider this billiard, then it has scatterers for one particle. For one particle, you have 1, 2, 3, 4 scatterers. And for the other one, you also have 4 scatterers. But if you consider the 2 together, then the scatterers are really cylinders, because the scatterers I determined in the configuration space of one center or the other center. And if you consider a scatterer in terms of one center, then for this one center, you have the hardcore condition that it cannot get closer to the center of this point. To this point, you have it's a circle, but the center of the other particles then can be arbitrary. So this is why it's a cylinder. And also for the other particle, so you have actually these cylinders, and also in addition, there is one additional cylinder, the condition that the two centers of the moving two centers cannot get closer than the twice the radius of the moving particle. This is already a cylinder given in terms of both centers, and it's also a cylinder. So this is a four-dimensional billiard with cylindrical scatterers. I don't want to go very much into the detail of billiard theory. Billiards with strictly convex scatterers are called dispersing billiards, and billiards whose scatterers are convex but not necessarily strictly convex, they are called semi-dispersing billiards. That's the usual terminology. Now, a cylindrical billiard is, of course, a semi-dispersing billiard. Now, what the situation is that, as I mentioned to you, in this upper philosophical, I would say, results of Hirata and so on, mixing rate ought to be known. Now, for four-dimensional billiards, no mixing rate is known. The situation is the following. For two-dimensional billiards, two-dimensional dispersing billiards, Sinai billiards, there is this great paper of great result of Lai Sang Yang from 96. Probably it was published in 98. And it says that you have an exponential decay of correlation for Hölder function, piecewise Hölder functions. So this is the famous paper, the introduction of these Young towers, and this construction is used in a lot of other examples. But this is only two-dimensional. And Balint and Toth were trying to extend this construction to higher dimensional situation, which is a very hard problem, so hard that they could not do it completely. What they could do, that assuming that the system satisfies an additional condition, the so-called complexity condition, which I will not define, of course, now. Assuming the complexity condition, they could prove that a multidimensional dispersing billiard has exponential decay of correlation. So it's very nice, but it's only hypothetical, so we cannot use it. Now, what we want to use, I will tell it later. Actually, 4 years ago with Peter Toth, we started to think about this Gaspard-Gilbert model. So this is just the repetition of what I have said. These are some notations. So the phase space depends on epsilon. And so this is the binary interaction. It's the cylinder of binary interaction. So if it's less than 2 rho m, this is actually the scatterer. And now you denote the successive binary collision times, tau 1, tau 2, and so on. Then, actually, this is a conjecture that if you take E1 and E2, these are the two neighboring cells, and these are the energies of the first one and second one. On this time scale, it converges to a jump Markov process on the state space E1 plus E2 equal 1, because this interaction, of course, conserves the energy. So E1 plus E2 can be assumed to be constant 1. And so this is in philosophy, it's related to this Hirata type results because you have a small set. So if epsilon is small, then this cylinder corresponding to the binary interactions is small, and so actually you get to a small set when there is an interaction, and when there is an interaction, then you can determine the transition kernel. So how the energy, how for example the energy of the first particle changes. So if E1 minus denotes the incoming energy of the first particle into when it goes into a collision, and this is the outgoing energy, then this can be calculated, and it can be obtained rigorously if one verifies Boltzmann microscopic Ray's property. I don't want to tell much about it. I just mentioned that this kind of calculation goes back to Boltzmann. So Boltzmann were considering a system of large system of particles, and he had to, when deriving the Boltzmann equation, he had to derive what happens after one collision with two particles. And for this, he derived a collision kernel which depends on the interaction potential of the particles. But in the case of hard core, so hard disk or hard balls, you have a special calculation. The essence in this Boltzmann derivation, and practically it is the same thing in our model, that if two disks or two balls collide, and if you know how they collide, so at which angle, with which velocities and under which angle, how they meet, then you can calculate everything. But you don't know this, it would be very complicated, but you have to make some averaging, and this is the microscopic chaos property. Okay. And in fact, in this model, the rate of, I told you that the rate of the binary interaction tends to 0, so it tends to 0. That's a calculation like the third power of epsilon. Now, the proof which we envisioned then, and we are still working on that line. So I told you that the four-dimensional billiard, semi-dispersing billiard, you don't know mixing rate, so you should get another way around. But in this model, you have the following hope, that most of the time the two disks evolve independently. Only very rarely we have seen that epsilon power 3, they interact. And during these times, there is an excellent averaging, excellent statistical properties for each particle. And one can try to apply a method similar which Chernov and Dolgopyat were applying. I just mentioned briefly the model they were considering. They were considering they were considering a billiard model. So this is a toric billiard. And they had two particles. Both particles were moving particles. One of them was a disk with mass m. This is the velocity, say. And the other one was a point particle with mass 1. And they were considering the situation when m tends to infinity. And they were using this standard pair method, which was very efficient. It's really a fantastic method. So I told that binary collision, most of the two disks evolve independently. Between two binary collisions, there is an averaging in each of the cell. And for this typically long time, it's natural to apply the Chernov-Dolgopyat averaging. They have this memoirs of the American Mathematical Society, Brownian Motion 1.
What is the long time interval that does not interact with this model?
Sorry?
For instance, in this model that you have one with large mass and others
Yeah.
small, which is the long time interval that do not interact?
Well,
One small, slow.
in this model, m tends to infinity, and wait a minute. So the situation that if m is equal to, Enrique, if m is equal to infinity, then this is a scatterer. And then this is a two-dimensional beautiful billiard. And for a two-dimensional, there is Lie-Sang-Yang, exponential decay, so you know everything. But m is not infinity, it's close to infinity. So until it doesn't move much, you almost have a billiard. So for some time, you can apply this kind of averaging. But if this particle moved already some not too long distance, then you cannot already apply it because it's a different model. And so this is what they did in this big paper, that of course if you want to handle this situation, you have to understand how much the model changes when this large particle is moved a bit. So you should understand a lot about the robustness, and this is what they did. Differentiability of SRB states leads to this kind of ideas. Now, so finally, so the task would be the following. So stable pair. So in this Chernoff-Dolgopiat model, a stable pair was the following. For the two-dimensional billiard, you take an unstable curve in the phase space. Okay, so this is a two-dimensional billiard. If you consider the Poincaré section map, then it's a two-dimensional map. And there you take an unstable curve. And on the unstable curve, you take a probability density. Nice probability. Everything is nice. So this is L, it's a standard pair. Okay? And they were introduced, they decomposed the whole phase space into families of standard pairs. So this is what they call the proper family of standard pairs. And what they had to show that an incoming proper family of stable pairs goes into a proper family after one collision. Collision is a drastic interaction, I repeat, so that's the difficulty. Now, in their case, this was possible because if M is very large, then this whole higher, this is also a four-dimensional billiard. But the four-dimensional billiard is very close, so all the cones are very close to the invariant cones of the two-dimensional billiard. And this is why it was possible in 200 pages. Now, in our case, this is not so. This is why we are still trying to work. And this was our first model. So one considers a paradigm model. So the in-cell dynamics is a billiard in a compact constant negative curvature situation. This is the joint work with Péter Bálint, Péter Nándori, Tamás Tasnádi, and Péter Tóth. So this is the Poincaré disk of the hyperbolic geometry. And then in this geometry, you have also hyperbolic torus. For example, this octagon would be one hyperbolic torus. So you put two pieces, this would be one and this is the other one. Of course, these are octagon. I cannot draw so small octagons, unfortunately. And then you have two moving particles whose distance is 2 times rho critical, or a bit larger. So this would be a sort of paradigm model. In this case, the phase space is a 4-dimensional hyperbolic billiard. So the phase space is 7-dimensional, and so on and so on and so on. I don't go into detail because for this model, we proved ergodicity and Kolmogorov mixing. This we could prove, but we couldn't go further yet. That's why we had to even simplify the model, namely, and this is the model we are at present working on. You take the following. So this is, now we forget about hyperbolic geometry. So this is a regular dispersing billiard in 2 dimensions. So this is the billiard domain, Q. And for the other particle, you take the position. It's a 1-dimensional, it's a sort of piston. So the particle moves along this interval, and the particle is a stick. And in this billiard, you have a point particle. So you can imagine that if this stick enters the billiard table, then it can collide with the point particle. And if this distance is small, then it's a rare interaction. So this is the model. This corresponds to the rare interaction limit, but it's not 2-dimensional, it's 3-dimensional. And we could calculate this transition kernel and transition rate. Now, yes?
How do you exchange energy with the piston? I mean, I understand the piston somehow.
Okay, so it's mechanical. Yes, I should have said. So here is the energy exchange. So what happens that this particle has 2 velocity coordinates, Vx and Vy, okay? The vertical velocity of the left particle remains invariant under a collision, as we know, and in the horizontal, there is just energy exchange. So the masses are equal, and then interaction just means the exchange of velocities. This is the mechanical model, okay?
Right, you measure they stick for a second.
Yeah, so it's...
So the stick is not changeable, so they hit the particle. So when the particle hits the stick.
They hit each other,
Yeah.
and this is the mechanical rule of the
It's got little dent.
momentum,
When you hit it, you actually
momentum and energy conservation. This is the solution. And
yeah, when I say that this is a piston with friction.
no friction.
Well, yeah, but friction with the particle. Otherwise, you wouldn't be able.
No, there is no friction. This is a collision. Joel Lebowitz were considering this kind of models. Exactly, and collision at the other end. Well, periodically until there is a collision. Then it gets a new velocity, and then it moves again periodically. Yeah.
This is what I mean by friction. If it gets a new velocity by a slanted collision with the particle, it means there is an instantaneous friction.
Okay, you can say that. But the important thing is that there is an energy exchange. That's important. So if you can solve this model, then you have hope to continue it periodically, and you consider an n-chain of these things. So we could calculate everything.
Sorry, assume that it's autonomous.
Piston do not?
If the piston don't care about the particle hitting the, so sometimes your particle is hitting with something that have negative curvature or something.
No, we don't have negative. So this is Euclidean model already.
I know, but it was convex. I'm saying.
Oh, yes. So this particle is a very beautiful, absolutely hyperbolic motion, billiard. Yeah. And there is energy transfer, energy exchange. So that's the good model.
So that is the natural particle is really small compared to the piston, it will remain hyperbolic.
Yeah, sure. This is also, it's ergodic. So it's ergodic and K. That's perfect. Okay? So what at present, I want to say what at present we are working on. Briefly I can tell the technical part. It's a big project, so this is the essential part now. Actually, in words, we have to prove a local limit theorem, local central limit theorem, and speed of convergence. So to bound the remainder term in the local central limit theorem. Local central limit theorem is the following. At school, one learns the central limit theorem, the Moivre-Laplace theorem. Moivre-Laplace for heads and tails. And in Moivre-Laplace, one learns that the probability that the partial sum is equal to some fixed value, it has a very small probability if you have an experiment that the order is 1 over square root of n times a Gaussian density. This is the Moivre-Laplace theorem, what one studies at school. And this is a local limit theorem. It's a finer result than the central limit theorem. So this is what I want to tell about it. And local central limit theorem, local versions of central limit theorem are obtained for billiards. So with Tamás Varjú, we obtained for a Young system under some conditions, natural conditions. Again, I am saying that, well, if you only, let's only consider the statement. The statement is, so you have a dynamical system and you have a Hölder function, say d-dimensional bounded and piecewise Hölder function. And then you take the partial sums of this function along the discrete time dynamics. And if you only consider this Sn minus Kn, it corresponds to really to the local limit theorem. Here the initial law is the invariant measure for your dynamical system nu. And then for gamma n, as I told you, in dimension d, it's of order. So actually this is not gamma, this is called epsilon, sorry, epsilon. Anyway, for this thing, it's of order 1 over n power d half, and you have a Gaussian density. So this is the local limit theorem, and actually we have a more sophisticated version, but in this derivation, I don't have time to explain why. We need this more sophisticated version. And so in our result with Tamás Varjú, we proved the local version of the central limit theorem when we start from the equilibrium, from the invariant distribution. In another paper with Gyima Dolgopyát, we needed an improved version of the local central limit theorem, namely, you don't start from the invariant distribution, you start from the standard pair. So you start from an unstable curve with some nice probability density. Of course, it's a harder question technically, but the claim is the same. And so what we now work on is the same thing where we have to obtain a remainder term. I just want to mention that Françoise Pen in a paper 4 years ago, she could prove a for local limit theorem with remainder term of this form, so which is a very good, but she proved this for the discrete free jump vector of a billiard, and it simplifies life because if you start from this Young construction, then along stable manifolds, the discrete free jump vector is the same. This is what I can tell about it. And these are the tasks, but probably I don't go then to these details because I want to tell some words, only some words, about our activity about the second half of the problem. So So assume that we can fulfill the first part of the strategy. So from the kinetic equation for the full description, microscopic description, one can obtain this generator of this Markov jump process, okay? In this rare interaction limit. And then, so now here x1, xn, these represent the energies. These represent the energies, E1 and En were before. And it has a generator, and with Grigo and Hanin we introduced a general class of generators. A is a test function, lambda is a rate function depending. So you see this resembles to our model. So this is the rate for along the ice binary ice bond. And there you also have a kernel which depends on the incoming energies, and there is a random choice alpha, and alpha just says the following: if you selected alpha, then what you do, that x, so this is the total energy of the two neighboring particles, and then after the interaction, alpha part of the total energy goes to the first particle, and 1 minus alpha part goes to the second particle. So this is the energy exchange. And then it's easy to see that the total energy remains invariant. There are some simple assumptions that this transition kernel is symmetric with respect to 1/2 and is not degenerate. And actually, the Gaspar-Gilbert model in dimension 3, it satisfies our conditions. So it's a special case of our general generator. They're calculated, so you can see. I don't want to talk very much about the special form. So the essential thing that the generator in the Gaspar-Gilbert model, not only in dimension 3 in arbitrary dimension, but in dimension 3 the formula are simpler. So they belong to our class. And what we proved that our result was that we characterized the reversible, non-degenerate reversible invariant measures for this dynamics, for this Markov generator, which is a fundamental fact. And it's the product of gamma distributions. We proved that there exists a unique stationary distribution on this. You know, the energies are fixed for the model, so on this simplex, our dynamics is given on this simplex. And so we could characterize these invariant distributions, reversible distributions. And we could also prove that we could also give a spectral, go bound on the spectral gap. And actually this bound says that 1 over n squared, constant time 1 over n squared. This is the spectral gap, meaning that one has an exponential decay of correlations, exponential convergence to the invariant distributions, and the rate is constant over n squared. And this is exactly the rate which is necessary to go further to prove the hydrodynamic limit. However, we had a condition that this lambda, actually I go back here. So I have to say that this was the rate, and the rate of binary interaction had this factorization. This was the form in Gaspar and Gilbert calculation. So there was a factor which depended on the sum of the two energies, and it was square root of the sum of the two energies. And it also had a factor which depended on the partition between the two the partition of energy between the two particles. It had this form, not so much interesting. And since here they had square root of s, this is why in the hydrodynamic limit one obtains square root of t, constant times square root of t for the coefficient of heat conductivity. So yes. So the important thing is that, so this 1 over constant over n squared, this is the appropriate, and actually there are situations when one can prove that you cannot get better. So this is what one has to prove. But we had this condition that the rate was bounded away from 0. So for example, square root of s is not bounded. So we could not cover, in this part of the result, we could not cover the Gaspar-Gilbert model. Actually, proving spectral gap, we just were using a pedestrian approach. But Makiko Sasada, in her invited talk on International Congress of Mathematical Physics, she could prove in general, so if the rate satisfies this kind of condition, so not only m1/2 but arbitrary non-negative power, then she could prove that you have this kind of spectral gap, constant over n squared, but the spectral gap also depends on on epsilon, and epsilon is the energy density in the model. So I return to here. So you see here, epsilon is the energy density, which is invariant because the energy is invariant. So what I started to tell that proving the spectral gap is a special science. So we just used for our result a pedestrian approach and we could prove it, but we learned out that several people work on spectral gaps, and it's a very beautiful branch of mathematics, and Sasada is an excellent representative. Okay, I think I finish that the difficulty of the second part, that the model is not of gradient type. Varadan had a fundamental paper for studying these systems, but in his case, this rate is bounded away from 0. So this is why it cannot be applied to our model. And Kipnis and Landim have this great book about hydrodynamic limit. And so with József Fritz, we are working on the second part too, and these are the difficulties. So I think, thank you very much.